So today we're going to talk about arcs and chords, and then you're going to have a quiz 2 school days from now on Tuesday. So one of the important things, or the new things that we're going to learn today, is something called the arc of the chord. So that's new. And an arc of the chord occurs when a minor arc and a chord share the same endpoints. So if you look at this inscribed polygon picture here below, an arc of the chord would be considered AB. AB is the arc, and then AB here is the chord. But it has to be for a minor arc. Theorem 9.1 says in a circle or in congruent circles, 2 minor arcs are congruent if and only if the corresponding chords are congruent. So this is really important. So 2 minor arcs are congruent if and only if the corresponding chords are congruent. So if I could prove that BD, segment BD, was congruent to segment ED, then I could conclude that arc BD is congruent to arc ED. All that same. Then I've drawn you a picture here of an inscribed polygon, in meaning inside. And for a polygon to be inscribed, every single one of its points has to be touching the circle. If one of the points isn't touching the circle, it's not considered inscribed. All right, so let's look at example 1. I want you to draw the following and add it to your picture. You might need a straight edge. You can kind of see the points that I put here. I want you to create a triangle using those points that I plotted on there for you. Tony, you can't turn that thing off? Where are you supposed to be every day at 8 o'clock? All right, then label these vertices A, B, and C. Now the directions say find the measure of each minor arc created when an equilateral triangle is inscribed in the circle. So if this is an equilateral triangle, isn't this congruent to this is congruent to this? How can we solve this? Equilateral triangle. What do you know about the degree of the whole circle? 360. These are equal. What does that tell you about the arcs? If the chords are equal, what do you know about the arcs? The arc of any equal chord is equal, right? So you might want to write down here, if segment AB is congruent to segment BC, is congruent to segment AC, then arc AB is congruent to arc BC, is congruent to arc AC. If I don't know what arc AB, BC, and AC are, but I know that they're congruent, I'm going to let them have a value of X. This is X, this is X, and this is X. If you were to set up an equation to solve, what would you do? What would you write? There you go. 3x is equal to 360 degrees. So then to solve, divide by 3. And then doesn't x equal 120 degrees? So therefore the measure of each arc is 120 degrees. What if I had a square in there? What would you do? Square, all 4 sides are equal, right? So if I inscribed a square in there, wouldn't you set up 4x is equal to 60, 360? You'd essentially divide 360 by 4. If I inscribed a regular pentagon, what does regular mean when I attach it to the name of the name of any polygon? What did you write with me?
All the interior angles are congruent.
And all the sides are congruent. So if I mention a regular polygon, a regular hexagon, a regular octagon, that means that all those sides are equal. So don't forget your polygon knowledge. All right, then look at theorem 9.2. It says in a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arc. Hugely important. If a diameter is perpendicular to a chord, then it bisects the chord and its arc. We will use that all the time. So, this one is kind of a bit of a hairy problem here, so let's look at it. In circle P, and you've got the picture here yourself, segment AB from here to here is congruent to segment AC. And you're told on the picture that this is 6. If this is 6, isn't AC also 6? So I've left that out for a reason. You'll see why in a minute. Find the value of x to the nearest tenth. Well, x is only this distance from P to, let's call this point here, I don't know, O. So you need to find the distance from P to O only. And I've got this little diagonal line in here from A to P. So here's what I would do if I were you. If these are congruent, and let's just connect this one. And if this is 6, and you've been told up here, isn't this part of a diameter? It's not the whole diameter, but isn't it part of the diameter? Aren't they telling you it's perpendicular to this chord right here? So according to theorem 9.2, doesn't that mean that this piece is equal to this piece? And that means that this has a value of 3, and this has a value of 3. Now I propose, or I theorize, that if these two are congruent, it's highly possible that this is congruent also. Not always true, but look. If this is 6 and this is 3, it screams 30, 60, 90 triangle. Because remember your pattern in the 30, 60, 90 triangle, you had 1, rad 3, and 2. Isn't 1 half the distance of 2? Isn't 3 half the distance of 6? So I'm going to test it and see. Watch how I test it. So we're going to put our pattern up here, 30, 60, 90. And the pattern is 1, rad 3, 2. Out of these two, this would be my hypotenuse, right? The 6. So wouldn't the 6 go underneath my 90? And isn't this the short leg on the triangle and this is the long leg? So if this is the short leg, what angle is it across from? The 30 or the 60? Which is smaller, 30 or 60? 30. So the 3 would go here. This is a fraction of 1/3. Is this a fraction of 1/3? Yes. So can't I put an x down here? And look, you do know that this distance, by the way, is 2 rad 3. But it's just the distance from here to here. We're going to use that in a minute. So I propose, oh, I guess we shouldn't use x. Let's use y. Why did I choose to change it? What do we already have here? Yeah, I don't want you to confuse the two. So I changed it to y. So if I were you, I would solve this proportion. So what is y equal to? Cross multiply, what's y equal to? 3 rad 3. So this whole distance from here to here is 3 rad 3. We want to find this distance from here to here, knowing that this is 2 rad 3. What do I do with the 3 rad 3 and the 2 rad 3? Subtract them. Wouldn't x equal 3 rad 3 minus the 2 rad 3? And what do you get for x? Just radical 3. That's about as hard of a problem as you're going to get. But you had to kind of recognize that, equal, it's possible that this distance here would be equal as well. So test your pattern. Does it work? It sure did. So that means this has to fall into that same pattern. All right, flip it to the back. We have one more theorem today. And this theorem says in a circle or in congruent circles are circles that have the same diameter or radius. Two chords are congruent if and only if they are equidistant from the center. So highlight that part. Two chords are congruent if and only if they are equal distance from the center. So we'll use that shortly. Now, example 3, crop circles. Anybody in here fascinated with crop circles? We don't live in farm country, do we? Anybody come from farm country? Did you have crop circles pop up around the area?
Yeah, probably for teenagers.
Probably from teenagers. What do people think about crop circles that live in farm country? Where do they come from? Aliens. It's true. I don't know. All right. The whole Mel Gibson movie. Did you ever see the Mel Gibson movie with the aliens and the crop circles? What? What's it? Signs, yes. There you go. This is Mel Gibson's movie right here. Here we go. You discover a crop circle in a nearby farm. A chord of the circle is 500 feet. If I were you, you're not going to get a picture for this type of problem. Just let you know. So the minute they talk about a chord of the circle is a certain distance from the center of the circle. You need to draw a picture that looks like this, and you need to draw a right triangle in your picture somehow. Now they might give you a picture, and instead of drawing this hypotenuse right here, which this is crucially important that you draw that hypotenuse right there. And you're like, well, duh, of course I draw it there. Well, what part of the circle is this? The radius. I will guarantee you that they're going to try to draw the radius. If they draw the picture for you, they're going to draw the radius like out here. They're not going to finish off that right triangle. So they're going to draw a radius out here somewhere. Can't you put a radius anywhere you want to in your picture? Aren't all radii equal? You can move that radius wherever you want to. I could put it from here to here if I wanted to, and I'd still get the same answer. But you need to place that radius where it creates a right triangle with the chord. So the distance that the chord is from the center is this distance right here, because here's the center, and isn't the distance from a point to a line always a perpendicular distance? Didn't we learn that last semester? So this is your distance from the point to the chord, or sorry, from the center to the chord. This is your hypotenuse of the triangle. It goes from the center to one end point on the chord, and it creates that hypotenuse of the triangle. This is your chord. Now, going back to the previous theorem, isn't this part of a radius or a diameter? True or false? It's true. If this is part of a radius or a diameter and it's perpendicular to a chord, what does it do to the chord? It bisects it. So from this picture right here, you're not necessarily going to see the whole radius or the whole diameter, but you have to recognize that that's part of it. And anytime you have something coming from the center of the circle to a chord of the circle, it will and it's perpendicular, it will always bisect it. So I know right there, just looking at the picture, that those pieces are equal. So go on to read. A chord of the circle is 500 feet long. This is the chord of the circle. So I know that this piece right here is 250 feet. Bless you. And is 600 feet from the center of the circle. Okay, don't worry about the fact that it doesn't look proportional. Don't let that bother you. So that center, or that distance from the center to the chord is 600 feet. So we have the two legs to our right triangle. You are to find the length of the radius. Knowing two sides to a right triangle, how do you find the length of the radius? Pythagoras theorem. All right, so let's go ahead and use it. So we've got a squared plus b squared equals c squared. This is my c because it's my hypotenuse. My a, it doesn't matter which one's a. So we're going to take 250 and square it. We're going to take 600 and square it, and it should equal c squared. 25 squared is 625. When you square a 0, you get 2 zeros. 6 squared is 36. When you square 2 zeros, you get 4 zeros, equals c squared. So add these two together, and you should get 422,500 is equal to x squared. Don't you wish you had a calculator to take the square root of? Do you have to have a calculator to find the square root of this? Could you factor it out? Sure you could. Would I do that to you on a test? Probably not. Alright, so if you take the square root of both sides, and we're not going to do plus minus because the square root of a length cannot be negative in this picture. So x is equal to 600, it's a perfect square, 650 feet. So therefore, the length of the radius is 650 feet. Now, although I haven't used my 4 boxes, have I done my 4 steps? What does this represent? The let statement is your picture. A picture is worth 1,000 words. That's your let statement. This is your equation to solve. You're solving it. Answer the question. All right, so then I have for you the study guide. We're going to do a few more problems. Chase, was there enough for you to get one? All right, so let's look at your study guide. I just want you to note, by the way, that your study guide has this picture again. You can go through this yourself, but if this piece is perpendicular to this chord, we're all listening and paying attention and we're not socializing, because that seat's going to get moved come Monday. That doesn't matter. Not right now. All right, so just looking at that picture, I can tell that those pieces are equal. And again, they've chosen to draw that there. If it's missing, you can draw it in. If it's anywhere else, you can draw it in. And so you're going to find that out when we do some of these problems down here. So let's look at these right here. You have 3 equal chords, and they've kindly told you that this is 120 degrees. How are you going to find NP? What are you going to do? All you know is this. What else do you know? These are all equal, right? So if you don't know them, what do you let them be? X. Can you set up an equation to solve? What are these all equal? 360. So you got 3 x's plus 120 equals 360. You solve that. So did you get 80 for x? If x is 80, doesn't that mean that arc NP is equal to 80? Then look at number 2. Now do you remember that theorem right here where it said if two chords are congruent if and only if they are equidistant from the center? The picture that you see here for number 2 oftentimes is the type of picture you're going to see for that question, but, and this is how they're trying to confuse you, they would have had to put a congruent tick mark here and a congruent tick mark here. That would show that this chord and this chord were equal distance from the center. If you saw a tick mark here and a tick mark there, you would know that this chord length is exactly equal to that chord length. Do you see the tick marks there? So we may not make that assumption. What can you assume? If we're trying to find the whole distance from K to M, and they gave you that this distance from here to here is 12. This is important. Why? The diameter is perpendicular to a chord, and this is part of a diameter. What happens to the chord? It gets bisected. So if this is 12, isn't this 12? And so what's the whole distance from K to M? 24. All right, then for XY, what would be our first step? Speak really loudly because I have all this going on with me. What? Pythagorean theorem. If I use Pythagorean's theorem, I'm going to find this, right? So 12 squared plus x squared equals 20 squared. So 144 plus x squared equals 400. What's the square root of 256? Well, what's 15 squared? 225. That's less than this. What's 16 squared? What's 6 times 6? Isn't this 16 squared? So the square root of this, x is equal to 16. So if x is 16, and I need to find xy, what's xb? It's 16 also, because isn't it bisected because this coming from the center is perpendicular? So what's the distance from x to y? 32. All right, let's look at these ones that you have to draw your own picture. Suppose a chord is 20 inches long and is 24 inches from the center of the circle. Stop right there. The minute they mention that we are 24 inches from the center of the circle, I immediately will draw the following picture. And don't worry about making dimensions look correct. I immediately will draw a circle, a chord, a center, and a right triangle. I will always draw that same picture. And now I'm going to plug into that picture what they just told me. A chord is 20 inches. What am I most interested in about the chord? It's bisected, so this is 10, and then this is 10 should I need it later. And it says it's 24 inches from the center of the circle. This is the distance right here from the center of the circle, so this is 24. They want to know the radius. We're not going to go through all the work, we're just going to set up the problem, and I'm assuming that you could use a calculator or whatever to finish it. What are we going to use to find it? Pythagorean's theorem, right? Isn't that C? So your equation to set up to solve it would be 10 squared plus 24 squared is equal to C squared. And of course you'd finish that. Then look at 5. The important part of these are how to set it up. Suppose a chord of a circle is 5 inches from the center. Oops, stop right there. A chord is 5 inches from the center. Immediately, I'm going to draw that picture again. Same picture. And they told us that the chord is 5 inches from the center. So here's 5 inches right there. And is 24 inches long. How does that help me? I put 12 inches here, right? Because the whole thing's 24, split in half, it's 12. So isn't it exactly the same setup as the previous problem? There's your C. So you've got 12 squared plus 5 squared is equal to C squared. And you'll finish that later. Well, I'm not even going to make you finish it later. All right, look at the last problem. Let me see if I can get this up here. Suppose the diameter of a circle is 30 centimeters long and a chord is 24 centimeters long. Find the distance between the chord and the center of the circle. The chord and the center of the circle. Again, I read those words, chord and the center of the circle. I'm still drawing that same picture. Bless you. This time though, they said, suppose the diameter of the circle is 30 centimeters long. What do I do with that information? 30 centimeters long. Where does that go in this picture? Does the whole 30 go someplace or only part of it? Isn't this part of a diameter? It's a radius, right? So if the diameter is 30, what's the radius? So 15 centimeters would go here. Then it goes on to say, and a chord is 24 centimeters long. So doesn't that mean that 12, half of that would go here? The question is, to you find the distance between the chord and the center of the circle. Remember, this is the distance that the chord is from the center of the circle. So this time your x changed. It's no longer the radius. You still set up a very similar equation to solve. You still use Pythagoras' theorem, but this time you have 12 squared plus x squared equals 15 squared. Weren't all three problems set up exactly the same? Okay, so the important part that you learn about today's lesson is that if you've got something perpendicular from a center, it bisects the chord. You can move that radius wherever you want to. And anytime a chord is congruent to another chord, its arcs are congruent and vice versa.